So my name is Daisuke Kawata. I'm from Marat Space Science Laboratory in University College London. And I will show you some new exciting results with the new exciting data we have done in a couple of months ago. And so my collaborators are listed here. And in the audience, Joe Chica just gave a talk just a couple presentation ago. And also Mark Kruper and Joe Shibrook also gave a talk this morning. They're a collaborator in RTMS cell. And these are some of the collaborators, including my ex-student, Rob Grant and Jason Hunt, and Joe Bobby in Toronto, and Noriki Matsunaga and Juichi Baba in Japan. Okay, so I will start from this plot. And I was listening press release of Gaia DR2, and when this showed up, and I just said, wow, this is amazing. And this is the power of Gaia DR2, I think, especially for the galactic astronomer like me. And this is showing that solar neighborhood stars velocity field, and x-axis is rotation velocity, and y-axis is the radial velocity, and going outward, inward, rotating faster and slower. So you can see that, or I hope you can see. It's quite it's not like wow, but in my screen it's very, very good. And the podcast casting of the ESA was quite amazing. And but you can see some of the very fine structures. And so this is showing that the solar neighborhood stars having a very different, many fine structures in their velocity field, phase space distribution. So this is known in Hipparcos time. This is the individual stars, and these are sort of the contour image. So that's also telling you a quite big difference. And these features are known and named in Hipparcos time, and these clumps are corresponding to these names. But you can see that in the DR2 data, you can see further structures. Also in here, also even the Hercules stream, that's called the Hercules moving group, you can see some two structures, or even smaller one here as well. So there are lots of fine structures or lots of common group you can find in the phase space, like what Wing was showing that in low metallicity stars as well. But this is the solar neighborhood stars and mainly the disk stars. Okay, and further than that, and these Gaia group, Gaia collaborator followed up this and showing that in the fine structure in a different projection of the velocity, including this is making a big fuss in these days, and this is showing the particle velocity versus position particle distance. This is the disk plane, and you can see this like a spiragram-like feature if you color these stars in the rotation velocity. Basically, this is showing that in-plane motion is also coupled with the vertical motion. So this is amazing to see that. And in this detail, and the people are trying to explain why this feature comes up, including people in Oxford. So I also jumped in Gaia DR2 when I was listening data release press conference, and they were just setting up all the script to be ready. And what we came up is very simple. This is looking at the galaxy from above, and we are here. And if we look at the galactic center region or outer region, just taking these regions, so Gaia proper motion gives you a rotation velocity. You can see that. So that's very simple. So using Gaia archive and setting up the script, the Gaia archive is excellent. It's very fast too. I really recommend that. It's compared to the other database, Gaia data archive, ESA one is very fast and quite flexible. And so we have done that. And I downloaded and calculated the rotation velocity. This is what I found, and I was really amazed again with the Gaia data. And this is the radius. And the rotation velocity with respect to the local standard breadth, the solar distance. And these are bright stars, which is having RBS data, so you can calculate the rotation velocity. But these are all more fainter stars. You can only use the proper motion to get the rotation velocity, because I pick up only these regions. And so you can see the full of structures, and like up to 40 kilometers per second. I didn't expect these full structures in this map. And further than that, and you see that there are lots of it's a diagonal ridge features in these features, and you can even see that far better in lower luminosity stars. Also angle is changing as well. And these features are also corresponding to these moving group. And now we can not only in the solar neighborhood, we can really see that whole structure of these moving groups. Like Hercules streams, it's amazing one. These two features. Also, you can see this extension of that. And also this gap is also first time you can see that in a very large region of the radius. And the people, including Walter Denen and Lester, talking about this was maybe the signature of the outer linear resonance of the bar. But you can see this kind of features in everywhere now. So I think we have to think about what is the rotation velocity of the bar. So Gaia DR2 is already making people busy to really understand what this kind of feature means. And further, a bit more than that, we can even see from here is this vertical dashed line is I'm showing that in the location of the spiral arm. So we are here, this is the sun, radius of the sun, and these are radius of the Perseus arm, and these are the distance of the Scatum Centaurus arm, that's this big one. And you can see the velocity, so the rotation velocity is changing in here, in these two arms. And this is the distance of the Sagittarius arm, and you cannot see that kind of big gap. So maybe these two arms are very strong arms and affecting a velocity field around that. But these field is a Sagittarius arm, which is maybe not a very heavy spiral arm. So we can sort of start thinking about it. Of course, I'm not making a huge claim for that, but these data is giving us now sort of lots of ideas about the spiral arm feature too. And we can also look at the vertical velocity as well. And we see, again, the radius versus the vertical velocity in the bright stars and the faint stars. We can start, this is showing, these dots are showing the peak of the distribution in vertical velocity distribution in different radius. And we can already see that some fluctuations. And so I have a look at that, and then you can see very clear sort of waves, particle waves is going around in different radius between 5 and 12 kiloparsec. This is found in Schoenrich and Walter Denen in Gaia DR1, but they converted, they used the solar neighborhood stars and converted the angular momentum to the guiding radius and plotted like this. But now I'm just using the position of these stars and see similar features, including this small one they identified in this some small dip around there. So that's quite amazing to be seeing a consistent, and they seem to have done quite a good job. And okay, and these features looks like having a warp as well. So it's, these kinematical information gives us quite a lot about the structure of the Milky Way disk. Okay, so it means that there are lots of fluctuations and the rotation velocity is changing, so there are lots of perturbations going on. So it's Gaia DR2 is showing us the galactic disk is not like a happily rotating smooth disk, but it's lots of motion is going on. So people are now saying that it's perhaps we have a Sagittarius dwarf just next to us, very close to us, and just rotating around. So maybe they are having inducing these particle waves like that. And in fact, we see that in some of the concentration of stars in the outer disk. So that is consistent as well. However, these kind of Sagittarius dwarf vertical impact, if they are like making a perturbation in axisymmetric way, then you will see this kind of waves like we see that in the Gaia DR2 data, but there is no tilt in this radial velocity versus rotation velocity field. But in DR2, you see this kind of inclination. So axisymmetric perturbation cannot explain that. So we come up with some idea, perhaps non-axisymmetric feature, which means like a spiral arm, may be able to explain these kind of features. And talking about spiral arm, we are working like more than 10 years now, not 10 years, around 5 or 6 years with my PhD student Robert Grant and Mark Roper here. We look at the N-body simulation and look at the animation of the N-body simulation. The spiral arm is always keeps changing, so it's like we call the transient spiral arm and also winding. So the spiral arm feature is also changing like this, so having like a flapping like that. And so it's basically these can be acted as a perturber too. So we have Jason Hunt in Toronto have made some model of this transient and winding spiral arm, and then you have looked at an effect of those kind of perturber on the galactic disk velocity structures. So here in this image are showing the Gaia data, again, the radial velocity versus rotation velocities, and these are, the contour is his model, and you see that in these kind of lots of features and also inclination in the Gaia DR2 data in different location of the disk, in up to the 1 kiloparsec inside or outside. And then this contour is his model, and we can explain this kind of lots of features on this phase space distribution. So spiral arm may be able to explain this. And also this is the radius versus rotation velocity, like I showed that in our data. And then these kind of rich feature also can be explained by the perturbation from the transient spiral arm. But this transient spiral arm is only the in-plane perturbation, so we cannot explain the vertical velocity oscillation. So perhaps it's I think it's always good to have a combination of that. And it's a combination means the Seychelles dwarf is having a vertical perturbation, and they may induce the spiral arm features, and the spiral arm is probably perhaps like a transient spiral arm, like anybody simulation we see, and these two effects is making these features. And in fact, in the Shelvin Laporte recently showed his simulation, including Seychelles dwarf and also self-gravitating disk model, and that's what he's got. This is like an image what George showed in this morning. These are Gaia DR2 data and his simulations. This kind of combination of the Seychelles dwarf and the transient spiral arm can explain these features, although the quantitatively a bit off. So I think the theoretical modeling people still need to work to really getting consistent with DR2. But now we can do this kind of high level of a study and understanding how the disk is perturbed and how they are affected by the dwarf galaxies. So I think we are having quite big fun with more detailed understanding, a more detailed kinematical structure of the galactic disk. So thank you very much.
So it's really for clarification. Are you saying that the Gaia snail, the Gaia spiral pattern, could not be produced by the Sagittarius because the amplitude is wrong?
No.
Saying,
Sorry.
Saying
I
the
was.
problem can be fixed?
I went fast. I think it's as showed by the James and other people. I think if there is high enough resolution, and you should be able to explain these Gaia spiral, phase spiral, by the perturbation like Seychelles dwarf. But he couldn't because the resolution of his simulation wasn't enough. And perhaps that amplitude was wrong, or maybe the perturbation was too strong. So his model is self-consistent model, which is, I'm happy to see that they get quantitatively getting this kind of features. But if they have an even higher model, or also trying a different kind of Seychelles dwarf mass or orbit, and then you may be able to see this. So I'm saying this is going way forward, but I think we need a higher resolution simulation.
But it's clear that if I did that model and subtracted away the data, the residuals would be enormous.
Yes, I agree.
So
but
what I'm trying to find out is what I need to do to his model to get it to match the data.
Yes, and that's what they didn't. They only did the quantitative work. But this is the right direction, I think, as you probably.
Thank you very much.
Yeah, thank you.